Hi, everyone. I'm Nathan Lambert, and I'm excited to be talking to you about my PhD topic, machine learning for microsystem control. So we have microrobots. I showed up a few years ago. We have the Ionocraft here. It has tethers coming off of it, this crazy open loop motion. We have other microrobots. We've had various jumping robots. We've had various walking robots. We have various rockets. And what we want to do is take these to the next level and actually have controlled microrobots. So just to kind of get into the mood, we have some other microrobots we have. Here is a video of the walking microrobots cut right to the point where you could see it taking steps. And with a lot of these systems, you'll kind of start noticing trends that the motion we have generated to date is imperfect. And we want to take this and make it even better. So the last microrobot video that I'll show, very exciting, is the jumping microrobot. So this is another way of storing energy in these substrate springs, and we can get a lot of different actuation mechanisms. And the question then is, what is kind of limiting these from having intelligent behavior? All of the behaviors I've shown you to here are open loop. So why do we need learning? If you were to come into one of our labs, as many of you have, what you'll see is something like this. And this type of setup, when you see it, translates into a high cost per test environment. This is not only because grad student hours are expensive, but because we want to see progress in these technologies. If your experiments are not precisely motivated to get a specific outcome, that is a huge cost and time in development of the technology. And second, the systems have really difficult to model dynamics. Most of the systems we're testing have these wires coming off of it or other forms of tethers that modify the dynamics away from any first principle decision-making that we could make for the controllers. So we need something that can adapt to this scenario where we won't get many samples, and we need to be able to control in a broad spectrum of dynamic environments. So why would we need machine learning, and what is machine learning doing in the real world? So if you go ahead up and follow the news of computer science and machine learning, there's this company called DeepMind and other big companies out there that are getting some pretty high profile successes in machine learning. And this is often in heavily controlled or simulated tasks. And you can ask the question of like, what is the secret sauce driving these successes? And the technology behind most of them and my PhD is something called reinforcement learning. Here at Berkeley, I don't have quite the scale of Google, but we can really study reinforcement learning and understand how we could translate this into more domains. So reinforcement learning is a technique inspired by trial and error learning. There's a lot of links to optimal control with Bellman backups and dynamic programming, and also in behavioral psychology with dopamine in reward circuits. So what happens is that an agent takes an action into an environment, and the environment then transitions the state. You get the next state, and you get a notion of reward. Here, reward is R, and the mapping from a state to action is called policy, which is pi. And what we want to do is have an agent that can maximize some predefined reward function, no matter if the dynamics are changing, if we don't know the dynamics at all, or any of those combinations. And this can give us a lot of exciting capabilities when we take this to microrobots. So what's the difference between these big at-scale projects from industry and what we're doing with microrobots? Well, I said the word big, and microrobots are definitely small, but there are some interesting ideas where we could bridge the gap from one to many robots, and then we get really interesting analogous problems at scale and of equivalent impact. So if we start making more Ionocrafts, we're going to get 1, 2, 3, 4. We're going to make a lot of these. We want to have a lot of robots that work and, more importantly, can work together to accomplish bigger goals like search and rescue or dispersed sensing. And this is where the notion of a swarm comes in. When we have so many robots that it looks like this, no one grad student is going to be able to hand engineer policies for what to do to solve these exciting tasks. And we're going to need other techniques for learning. And what I'm interested in is this trial and error learning. And where we started and where I've spent a lot of time is on a specific variant of it called model-based reinforcement learning. And what happens here is there's a specific optimization step where the agent learns a model of the environment to use it as a structured knowledge of the world. So while an agent is improving, it acts in the environment courtesy of this policy labeled pi. And what it does is it collects data to learn a model of the dynamics. Here is an equation shown where you're maximizing the likelihood of a distribution to a next state from a current state in an action. There's other loss functions. Those are all different tools, but the methodology at a high level is what we're interested in. And then with a dynamics model, what we'll then do is we'll plan or use some other algorithm to make decisions to maximize this reward function. So R is really what we want the agent to maximize. And we have complex systems. These approaches still work in general. There's not much more engineering that we need to do besides scaling up. So what's a technique that we could use for model-based reinforcement learning? So if we have this equation where we can predict a trajectory, here F theta is a symbol that is often used to indicate the parameters that we were trying to optimize in our controller. So we can predict the next state, st plus 1, and if we repeat this, we can predict trajectories. So we take 1 step, 2 steps, many steps, which is called many compounded network passes, and there's some interesting work to understand what this will do to your predictions. But then what we have is we can have a bunch of simulated trajectories from some action distribution. So how do we use this to make decisions, and how do we use this to make the decisions that will improve over time by trial and error? So what we will do is we'll do this method called sample-based model predictive control on a learned model. We didn't throw some algorithm name at it. It's actually really simple. So we can unroll trajectories from an action distribution. And then what we were going to want to do is we optimize over a finite horizon. So we look at the action sequences that gave us these different trajectories. We were sampling over a matrix of different actions. And then what we were going to see is that they result in different trajectories. And we choose the trajectory that has the highest reward number from this function I was talking about earlier. We return that action sequence to the model, and we take that action in the world. And what we can see is that there's a discrepancy between the chosen sequence and the true future dynamics. But what we want to do is we iteratively retrain this dynamics model to get better at the task. So what's one way that we use this? So what we did is we took a crazy fly, which is a really small quadrotor, to kind of mirror it to the ionicraft. And we put low-level sensors on it. So an IMU, so we're getting roll, pitch, yaw, and accelerations. And then we wanted to see if we could apply motor voltages directly to do low-level control, like we were trying to do on these micro robots. And then we wanted to optimize over a finite cost. The cost is just the negative of the reward. We want a big reward or a small cost. And we had a simple cost function of minimizing pitch and roll, just to try to keep this quadrotor stable. And this is actually a video that you all may have seen in the past, but what you see is that the quadrotor starts by taking these random trajectories where it can barely do anything at all. It'll flip over instantly, and that's by design. And then we iteratively retrain this dynamics model of the world to get an understanding of the robot. And then over time, the cost function is achieved. So this is a simple proof of concept where we have a robot, we can do trial and error in the real world, and we can get interesting and compelling results. And what I'm here to tell you about is, and really sell you on, is thinking about what we can do to then take this method and apply it to other tasks. So where I started was talking about towards artificial agents in the wild and being motivated by what these big companies are doing and the successes that they're having. And what we need to do is kind of pick the specific problems where we can have as big of an impact on our work and keep transitioning these technologies to the real world. So if this was on this quadrotor video I just showed you was low-level control. So if we go back slightly, we're sending via radio motor voltages that are really a function of this neural network dynamics model. And we're choosing the best one to maximize reward. What else can we do with this framework? So what we can do is, instead of learning control voltages, we can learn behaviors. So the optimization change here, you can see at the bottom, is we're going from controlling motor voltages to controlling control parameters themselves. So we can think of that as something like a PID parameter, an LQR parameter, some other type of gate parameter. And this is just going to show you how you can use model-based RL in a bunch of different tasks. So here we're kind of going up the levels of abstraction, where the tasks might be conceptually harder for an engineer, but the impact can be even greater because you can scale this to more robots. So another step that we can take is we can go from low-level controls to behaviors, and next we can go from behaviors to design. So what we can do is we can also include the physical design parameters of the robot or of some other system from your BSAC member project, and we can put that into the same model-based reinforcement learning optimization framework. So what that means is that instead of choosing motor voltages, you'll choose something like a leg length or a number of linkages. And the same data efficient trial and error process will be used because it is an open-ended reward optimization. So whatever the inputs in the search space you give it is, it'll be able to optimize over that in a data efficient manner to get you the outputs that you desire. So this is really exciting that we can go from low-level control to high-level design, all with the same methodology. And this is all from work from our group. And the question is, where does this trend continue? And something that I've never seen in my 5 years of BSAC and talking about microrobots is that there's a lot of pop culture references to where microrobots
The applications for this tech
are. So this is from Big Hero 6. And if you haven't seen this is the best advertising for microrobots out there. And we want to create a reality with this. And as our actuators and as our robots get more advanced, we want to be able to use them to imagine the future like this. And I think model-based reinforcement learning is just one step along this path. And we really have to embrace machine learning in order to make this a reality. So to conclude, as I get my position. To conclude, there are really a few key points that I'm trying to get across. This talk is really focused on the high level of we want to create a future with machine learning that is integrated with microsystems. The low-level details you can work out, you can talk to me, you can talk to a researcher, but it is inevitable that machine learning is being taken up in many different fields. And if you want to have an impact and be on this cutting edge, the time is now to adopt it. And microrobots are still really hard, which is why we had to focus on the data efficiency of some of our methods, which is why our group has been working on model-based reinforcement learning, because learning a structured model of the dynamics takes less data than other optimizations that are totally open-ended. And finally, as we scale up our micro technologies and they work together in groups, that scale lends itself to be even more impactful when using machine learning because they're even less tractable when us engineers are trying to do it by hand. So thank you for your time watching this talk, and thank you for working with me over the 5 years. This might be the last time that you see me, and I will happily take your questions now.